It's the first time humans have been able to excite nuclei with a laser. And so that's going to bring the techniques of quantum control, quantum computing, to the nuclear degree of freedom.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. We measure time and set many standards by using clocks. Clocks that work by counting a periodic event with a known frequency. Examples include old-fashioned grandfather clocks and their swinging pendulums, or the wound springs of a mechanical clock, or the vibration rate in a quartz wristwatch. Any of these methods can become inaccurate over time. So since 1967, atomic clocks have been used as the standard to set time, specifically using cesium-133, as atoms are naturally resonant at very high frequencies, allowing them to be very accurate over long periods of time. But what if it were possible to have an even more accurate way of keeping time? We're joined by Eric Hudson, a professor in the Department of Physics and Astronomy at UCLA, who has spent the last 15 years working to accomplish the seemingly impossible, directly manipulating the energy level of an atomic nucleus using a laser, something that has never been done before. The result of this work may unlock the most accurate clock ever and allow advances in communication and deep space navigation. Professor Hudson, thank you so much for joining us today.
Thank you for having me.
So I like to kind of set up background usually, but I think in this case, we need to define some of the terms as we're moving ahead. So in my intro, I just mentioned that we've been using the atomic clock since the 60s as kind of our definition of what time is or how we mark time. So what is an atomic clock?
It's a really good question. And I think to answer it, you actually need to back up and think about just a regular clock first. We all have an inherent understanding of what a clock is. They're very important in our lives, but we don't really think about them too often. What they're doing is pretty profound, right? Evidently, there's something we all agree on called time, right? And the time is later now than when we started this discussion. But how do we measure that? How do we agree upon how much time has passed? And what we do with clocks, we typically have some sort of process that repeats itself, and we assume that repetition is sort of constant in time. So think of a grandfather clock, where you have a pendulum swinging back and forth. Now, we might construct that thing such that after one oscillation back and forth, we call that 1 second. Right? And then you can, let two oscillations be 2 seconds, 60 be a minute, and so on. The wristwatches or our phones that we use, they typically have something very similar to this. It's a piece of quartz that vibrates at about 30,000 times per second. But it's the same idea. You just count up to 30,000 and you say, okay, that's a second. So you could see a lot of details in that analogy that are going to be important for understanding atomic clocks and eventually nuclear clocks. The first is, it helps to have something that's vibrating or oscillating at a higher frequency. Because if I miscount, it's not a big deal, right? If it's a grandfather clock that goes once per second and I miss one, then I'm off by a factor of 2 in my time. But if it's a quartz oscillator that's 30,000 times per second, if I miss one, it's not as big a deal. So a higher frequency oscillator is a good thing. The other thing that's important is that our clocks be identical. If you and I build grandfather clocks, and I make my arm a little bit longer than you, or my bearings maybe not as good as you, there's a little more friction, right? Then my clock will run slower than yours. If there's a lot of friction there, for example. And so after some time, we no longer agree on how much time has passed. And I'll show up for this interview late and you'll move on without me. So that is where atomic clocks come in. The brilliance of atomic clocks is that, as far as we know, every, let's say, hydrogen atom in the universe is identical. So hydrogen atoms here in LA, on the East Coast where you're at, or in another galaxy, they're all exactly the same. And what that means is they absorb and emit light at exactly the same frequencies, right? So we know you can shine in a laser, for example, and excite an electron in an atom to a higher orbital, and that happens at exactly a certain color of light, right? For example, the sodium, like the street lights that are orange, those are sodium atoms, right? And that's that orange color. I'm pretty sure that's correct. You should check that before.
I think so.
I think that's correct.
If not, we're both wrong.
Okay, we could cut that part out or leave it in. But so nonetheless, these hydrogen, or all these atoms absorb and emit photons at exactly the same frequency. So if I take a laser, for example, or maybe I use some other transition that doesn't really need a laser, but as long as I'm driving some transition in this atom, then in the case of a laser, I have to have that laser at exactly a frequency that's determined by nature, right? And it's the same here as on the moon, as in Andromeda Galaxy, if I'm driving, say, a hydrogen transition. So if I make sure my laser can always drive that transition, now my laser, the electromagnetic field of the laser, is oscillating at a frequency that's tied to the structure of hydrogen, which is set by the laws of the universe. And so my laser now becomes my oscillator. And if I count the oscillations of the electromagnetic field, I can use that to keep time. And that can be very high frequency in optical atomic clocks. It can also be identical because all the atoms are the same, of the same type. So our clocks are guaranteed to tick with the same frequency. And importantly, because, we have techniques now where we can isolate these atoms from their environment, we don't have this problem of like friction in the pendulum clock anymore.
Right.
And so these things aren't going to be perturbed by their environment as much. And so we can build these, amazingly accurate clocks that people have built.
So what is the difference in approach with a nuclear clock?
So the nuclear clock is very similar in the respect of using a laser, for example, to drive a transition, and then the laser as your oscillator. The difference comes in what aspect of nature you're talking to. So in an atomic clock, what we're doing is we're exciting electrons. So if you think of the Bohr model of the atom, we have some nucleus with protons and neutrons. We have electrons around it that are orbiting it. And we know that those orbitals have well-defined energies. We can send in a photon and excite that electron to a higher lying orbit. And that is exactly the transition we use in an atomic clock. In the nuclear clock, we're not exciting the electrons anymore, but we're exciting the nucleons, the neutrons and protons inside of the nucleus. And this has several advantages. The first is it's just cool. It's right? Humans haven't been able to excite nuclei with lasers before. And the reason is that those nuclear excitations are typically really high energy. So, gamma rays that we worry about with radioactivity, that's where they come from. They come from, when a nucleus radioactively decays, it produces another nucleus that's typically in some excited state. And so those neutrons and protons emit gamma rays as they relax down to the nuclear ground state. And so those are, in terms of energy, that's what we call a kilo or mega electron volt. Whereas the energy of a typical photon that we see is sort of an electron volt. So these are 1,000 to 1,000,000 times more energy. And so we just can't build lasers yet at those frequencies. But in thorium-229, due to some fluke of nature, it's the only isotope in all the known isotopes. The first nuclear excited state is only about 8.3 eV. So this puts it at about 148 nanometers. This is light that you and I can't see with our eye, but it's still light that we could generate with a laser. And so the idea then for the nuclear clock is you excite, say, that valence neutron to another orbital, and you use that transition energy as the reference for your laser. And this has some advantages. One is it's an even higher frequency transition than what we have in optical clocks right now. The other is what you want is a very narrow resonance feature, so that you have a very well-defined frequency. And this transition is narrower than basically all the ones that are being used right now. But more importantly than that is how sensitive it is to its environment's perturbations. I told you earlier, one of the great things about atomic clocks is we can isolate them. They don't care about the environment. That was a little bit of a lie. They of course still feel the environment. Black body radiation, magnetic fields, things colliding off the atom, those all perturb it. So these sorts of systematic effects are really what limit clocks' sort of ultimate accuracy. For the nuclear clock, effectively because the nucleus is so much smaller than the electron cloud in an atom, It's just less sensitive to all these things. Magnetic fields, black body radiation, it just doesn't care about them. And so it may prove to be a significantly more accurate clock.
So why would a more accurate clock be beneficial? And I guess this gets to, why is measuring fundamental constants more accurately such a big deal?
Yeah, so I think that's a great question. And I think there's two answers to that question. One is the technological impact and one is the scientific impact. For the for the technological impact, precision timekeeping is actually really important in our daily lives. We don't normally think about this. If you're a minute late to a Zoom meeting, it's okay. But your cell phones, your global positioning, lots of communication technology, some imaging technology, you really have to have the most precise clock you can get. And if you had better clocks, you could do those things better. Like if we had better atomic clocks, GPS would be better. That is important for, navigation here on Earth, but also as you go into the solar system and beyond, this sort of deeper space navigation, this becomes a really big problem. So just broadly speaking, having better timekeeping is going to make navigation, communication, things like this better. So we'll have better technology. For the scientific part, which is the part that really excites me, you mentioned this idea of the fundamental constants in nature. To understand the impact there, you have to back up for a minute and think about what these fundamental constants of nature are. Right. So we have things like, we know that there's gravity. We know that two like charges repel. And we have theories that explain that to depending on, well, maybe not gravity, but for at least for the charge repelling, we have that explain this to really high precision. However, those theories have the input parameter. In the case of electromagnetism, it's something called alpha. It's about 1/137, the fine structure constant. And it's a number. And it's just a number that is in our universe. Like that's just how strong electromagnetic interactions are in our universe. We don't know why. We don't have a theory of it. We just measure it. And it's that. And it appears to be constant over the measurements that have been done by humans at about 1/137. And as the name implies, we think that they're constant at the level we've measured them so far. But given that we don't know why these things are the values they are, or even like where they come from, really, it's a really interesting question to ask, are they really constant? Or are they just constant at the level we've measured them? Because everything we've looked at in nature, the closer you look at it, the richer it is in some sense, right? There's more stuff going on. So could these fundamental constants of nature vary? To contrast that now to the nucleus. Inside of the nucleus, the energy scale of the nucleus is mega electron volts. It's just much more tightly bound. There's the particles have much more energy. So if the fundamental constants inside the nucleus that govern the nuclear force, which include the fine structure constant, though maybe this transition it's not clear how sensitive it is to the fine structure constant or if it's more sensitive to the strong force constants. It's sensitive to these constants somehow, of course. But if these constants say change by 1%, instead of changing by 1% of an EV, they change by 1% of a mega electron volt. So it's a million times larger shift. And so it'd be much easier for us to see that with our lasers. And so it's already, now that we have the ability to drive this nuclear transition, we can measure these transitions now, and in a year or so, measure them again. And if they're the same, it will be the it'll be the strongest constraint on the variation of the fundamental constants by a long way. And it'll be hard, I think, within my lifetime to do much better.
Okay, so you're with the nuclear clock, you're talking about using thorium. And I think you mentioned thorium-229 specifically. Can we kind of explain what those are and what the difference between them are?
Yeah.
Like when the elements or isotopes have the numbers on them, what does that mean?
Oh, yeah. So the name of the element denotes how many protons are there. So, hydrogen has 1 proton, helium has 2, so on and so forth. Thorium is way down here on the periodic table, which I always have nitty on my desk. I don't know if you can see this here, but it has 90 protons. Now, the number that when people quote a number in front of an atom, like in the case of thorium saying 229, that's the total number of neutrons and protons. Now, the number of protons is fixed. For all thorium atoms, it's always 90. And the reason for that is if you change the proton number, then you change the electrons around it, and then that changes the chemistry, and we call it a different element. So everything that has 90 protons is thorium. You can have a variable number of neutrons. Neutrons are neutral. The nucleus can accommodate, some range of them typically. The sort of normal isotope of thorium, the one that if you go dig in the dirt, you can find is 232. So there's 232 nucleons or protons plus neutrons in this nucleus. The isotope that we're working with is 229. So it has 4 less neutrons. And what's special about this is that in all of the chart of the nuclei, it's basically the periodic table, but including all the isotopes. It's the only isotope that has a nuclear transition that's laser accessible that we know about. Most of them are keV to MeV, so 1,000 to million times larger energy. And so we're using thorium-229 because it's the only isotope in the universe that we know about that has this property. But that also means that you can't go dig it out of the ground because it all decayed a long time ago. So you have to get it from things like decaying uranium. And so as you can imagine, it's a hard to find people that can supply you with that. We determined the smallest amount we could use was about 3 milligrams, which is not much more than some dust.
Right. So you mentioned that it's kind of at a dust state almost. And I know you're needing host crystals as part of the experiment part of this. So can you talk a little bit about the process of making the crystal and why you need the crystal?
Yeah, no, that's a great question. So the sort of what's unique about the nuclear clock is that you can excite this nucleus even if it's inside of a solid, right? Now, this may not sound too surprising coming from outside the field, but inside the field, we're just not used to thinking about that because we normally are driving electronic transitions. And so there we all have atoms that are basically in vacuum. They're just isolated from everything else. And the reason is if you put them in a solid, their electrons form chemical bonds with the rest of the solid, and the transition you're just driving disappears, right? You don't have these super narrow lines. But the nucleus doesn't participate in the bonding. Whether it's in the gas phase, a liquid, or a solid, it just kind of looks out and sees electrons around it, and its nuclear levels are there. And so that means we can drive it inside of a solid, provided that solid has what we call band gap. And that is basically, it's transparent to the light that would be needed to excite the nucleus, right? So that's why we call these crystals, because they're beautiful little super clear crystals because they're transparent to light. And this could be a really nice simplification for clocks, because instead of having, I don't know if you've seen atomic clocks, but most of them, at least the optical atomic clocks, are room-sized type of apparatus, and you can make them smaller, but they're still. With this solid-state clock, we could replace that with just a little crystal, because we don't need to do all this stuff to trap and isolate these nuclei.
Right. And I'll know for people that are listening or watching this interview right now, the other laser physicists we've talked to are approaching it in the way you just described, where it's in a vacuum state. So that's one of the things that's interesting here, is having it kind of in a crystal structure. Yeah. Okay.
And of course, you could do this in a vacuum state too, and that probably will be the best clock, which, a place like NIST would probably want to build because they're going to keep time for the nation. But if you're going to put a clock on a satellite or something, the crystal might be a really nice way to go. So then how do you make this crystal, I guess was your question. Carefully. And that took many years. It took about 5 years before we successfully got thorium into these crystals. The way you do this is you basically, it's like baking a cake. You take all the atoms that you want into the crystal, you sprinkle them into a little container, and you just heat it up until it melts. And then there are different ways of crystallizing it, where you effectively what you do in one way or another, you slowly cool the thing down and it grows a crystal, kind of like if you ever let salt evaporate or water evaporate from a salt mixture and you grow little crystals. It's not so different than that. And then you have to cut and polish these things, and all that's a little bit challenging because it's radioactive. But after a few years, those were overcome.
I'm imagining you had to test out a lot of different materials on the way to finding what worked.
We did. Yeah, there's a lot of competing constraints or requirements for these crystals. They need to host thorium. Thorium's a very big atom, so a lot of crystals don't want it in there. It takes up too much space. The thorium's radioactive, and so when it decays, if the material scintillates, that is, there's radioactive particles going into the crystal, often these crystals will glow. Like, you see these like little, radioactive like china and things that are just that glow, right? That's bad for our experiments because we're shooting in light and we're looking for light. So it'd be nice if it didn't glow. There's just all sorts of constraints. We looked through many different types of crystals before settling on the one that we use in this study, which is lithium, strontium, aluminum fluoride.
This term I saw in the paper, and I don't really know what it means, so I'm just going to ask it. What is a vacuum ultraviolet spectrum?
No, that's a great question because that is a bit of jargon. It's a very simple concept with the word is much longer than the concept. So the electromagnetic spectrum, goes, we have gamma rays on the high end, radio waves, for example, on the low end, and in the middle somewhere is the visible, depending on where you define the middle, right? And so, with our eyes, I don't know, depending on who you are, you can maybe see from, 400 nanometers, maybe a little below, up to maybe 800 nanometers, right? So that's sort of like from, like violet to red, right? Below that is what we call the ultraviolet. Right. This is the thing we worry about when you go to the beach, and especially if you have hair like mine, you want to wear a hat or put on a lot of sunscreen. And that maybe goes, depending on who you ask, maybe from 300 nanometers to, let's call it 190, 180 nanometers. And that's light that can propagate through air. It's just we can't see it. It's very high energy, and that's what the problem with skin cancer is, that it can hit our skin and cause bad things to happen. So below let's say 180 nanometers or so, that light no longer propagates in air because it gets absorbed by the atoms or the molecules in air, like oxygen, for example. And so that region, we don't call the ultraviolet, we call it the vacuum ultraviolet because it only propagates in vacuum. You have to suck all the air out of the room if you want to shoot a laser beam of this through. And so that's why in our case, this stuff is the crystal and the laser light is in vacuum, just simply so we can get the light to it without the air in the room absorbing the light.
So bringing all this together a little bit, it was something like 15 years for this effort to come to fruition here, maybe longer. Was achieving your result a surprise to you, or did you always know it would be there waiting?
That's a really interesting question. So, 16 years, 15 years is a long time. So it's a slow burn. In the beginning, and I would say, I don't even remember now, it's kind of probably good. The first 5, maybe 10 years, many people doubted that this was possible. Because people thought that the thorium transition that we're driving actually didn't exist at all. They thought maybe the nuclear physics measurements that had said, hey, this probably exists, could be wrong. And so that was always a challenge of, and because of that, I shouldn't say this part. I was going to say because it's hard to get funding, but the NSF,
you have to convince people that it's that's part of the.
And because of that, you really had to convince people to fund you. And we're really grateful to the NSF for being forward looking and taking a risk on this. So. I hesitate with the dates, but I think it's about 5 years ago. There were some measurements that came. They weren't driving the transition, but they made it clear that this transition really did have to exist. And so the that part of the surprise was we weren't surprised about. What was surprising was, we've been looking for this for a long time, and we'd started to think that maybe there were fundamental flaws with this crystal mechanism. I told you this story that, when you put the thorium atom in the crystal, all you have to do is be able to get the light there and everything works. Well, there's a lot of other effects that could maybe happen, and we were really worried about those. And it looks like those do happen to some of the thorium atoms in the crystal, but maybe not all. And so I would say it was more of a relief than a surprise. But as it took a couple of weeks, I think, to sort of emotionally process the whole thing, because we've been sort of chasing this carrot for so long. It's like, what do you do now that you finally have it? And then over a few weeks after that, it just, everyone started to understand, like, hey, this is finally it. We can do all these things we wanted to do. And so since then, it's just been a flurry of activities, every day, fun results. It's a really fun time. I doubt I'll have too many chances like this to do this kind of fun science. So we're just really enjoying it right now.
To finish this train of thought, what's next with the work? What are your next steps from here?
Twofold mainly. The first is to start building clocks out of this. So this is getting narrow line lasers on this, putting all the clockwork around it, and just seeing how well they perform by comparing them to clocks that we have right now. The second, which I find really kind of exciting because it's a little more unknown, is what are the best crystals? What are the best ways of doing this? Are there techniques we could do to modify the crystal, or something about fields that applied to improve performance, and to make better clocks, make better measurements? And there, I think it's really fun, because I think what's going to come out of this is not only better clocks, but what we're seeing already is that there are effects of these crystals on these nuclei, and we can measure those. And anytime you can do that, you can turn that around and make a sensor. So I think we're going to see, my prediction is, totally new probes of materials. By doping these nuclei in them, looking at these transitions and how the material affects it, we're going to learn things about materials, I think, that we haven't been able to before. Maybe someday this will be like a standard technique for material characterization. But really, I don't want to say that. I was going to say the best things are unknown, but because that's kind of lame. But really,
it's exciting how much we don't know. Like if there's nothing else I've learned in having these kind of conversations, it's how little, like, the things that we think are set aren't necessarily. It's just what's been measured. Like you were talking about measuring things over a year. It's like 10 years from now, it might be measured in a totally different way and just totally flip over the table for how you understand it.
I think that's right. I mean, this is really, it's the first time humans have been able to excite nuclei with a laser. And so that's going to bring the techniques of quantum control, quantum computing, to the nuclear degree of freedom. I think it's almost unpredictable, all the things that are going to happen from that. It really is the opening of a new era, I think.
Special thanks to Eric Hudson. For the Discovery Files, I'm Nate Potker. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.